And it's kind of crazy to think that you make something cold by shining light on it. Normally we think about shining light on something and making it hot. Laser cooling does something quite counterintuitive. It makes something cold by shining light on it. Temperature is about motion. The molecules in the air in this room are moving really fast, about 300 meters per second. If you cool down a gas, you're making the atoms and molecules move more slowly. And getting to the lowest possible temperatures, that's the extreme that we're trying to go to on Cal, and we learn something new when we go to those extremely low temperatures.
We start with atoms that are actually room temperature, or even a little bit hotter than room temperature. We just have a vapor of them in a glass cell, where we use the radiation pressure from lasers to slow down atoms.
As it turns out, light pushes on stuff. We don't feel it when we walk out in the sunlight, but for something as light as an atom, the push that you can exert by shining light on the atom, in our case laser light, can be really significant.
We don't actually use 2 lasers, we actually use 6, so there's 2 this way, 2 vertical, 2 in and out, and so no matter which way the atom's moving, it's always moving towards one of the lasers, and that causes it to slow down and cools them down to 1,000th of a degree above absolute zero.
But eventually, to get to the temperatures that we need for Cal, we actually have to turn off the lasers. And what we do is we move the atoms so that they're held by magnetic forces.
And what we can do now is we can just adjust the magnetic field so that this trap that they're held in is not very deep. So we can make it so that the most energetic atoms just have enough energy to just move off and escape, and they fly away.
We can actually pull out just the hot atoms, leaving the rest of them at a colder temperature. This is called evaporative cooling. It's essentially the same as when you blow on your coffee cup. The hottest molecules make it out of the water, and if you can constantly be blowing those away, you can cool down your coffee. And that gets us all the way down to these temperatures of microkelvin, a millionth of a degree above absolute zero.
But it turns out you can get even colder by using another really old trick called adiabatic expansion. If you take any gas and you expand it, it'll get colder.
So we're doing the same thing on a sort of small scale. We have this little small sample of atoms that are confined by magnetic fields. And what we're doing is we're reducing the strength of that magnetic field, which lets the atoms expand out something like a factor of 1,000, which causes them to cool off by a factor of 1,000.
This trick works so well, we get down to temperatures below 1 nanokelvin, 1 billionth of a degree above absolute zero. And it's being done on the Cold Atom Laboratory every day.